Hello, I'm Ben, and this is my third paper review for Complex 52921B, Engineering Self-Adaptive Systems, Assignment 3. This paper is titled Uncertainty Reduction in Self-Adaptive Systems by Gabriel A. Moreno, Javier Cámara, David Garlan, and Mark Klein. It was published in the Proceedings of the 13th International Conference on Software Engineering for Adaptive and Self-Managing Systems in 2018. So firstly, what is the problem? Self-adaptive systems depend on models of both themselves and of their environment to decide when and how to adapt, and these models are often infected by uncertainty. This uncertainty causes the model's predictions of current and future states to often be inaccurate or to react in unexpected ways which cause larger problems. Two important kinds of uncertainty are those due to variability and lack of knowledge, also known as aleatory and epistemic uncertainty. The former is due to randomness, and the latter is due to gaps in the system's knowledge of itself and or its environment, which is specifically not due to randomness. Why is there still a problem? Well, current approaches consider ways of modeling and reasoning about uncertainty in order to better predict and consequently react to it, which is certainly beneficial. And while this uncertainty modeling certainly improves self-adaptive systems overall, there's still room for improvement. This form of uncertainty management relies on the engineer making a conscious decision to incorporate uncertainty into their model, as well as planning out exactly where these uncertainties come from and how to model them. The author doesn't speak to any related work in terms of uncertainty reduction, but they do speak to the topic of existing uncertainty management in the form of uncertainty modeling, as mentioned previously. Here's an example of how a current system may deal with uncertainty. Consider a system which must keep a variable, say temperature, below a fixed threshold. A naive approach might take a simple average of the observations, or a point estimate, to decide whether to adapt. And if that point estimate's below the threshold, it would decide not to adapt. A more intelligent solution, incorporating the fact that uncertainty almost certainly exists in the system, could use a confidence interval to determine if it's possible that, despite the point estimate being below the threshold, the actual variable could actually be above, and thus potentially prompt an adaptation that otherwise would have been missed. As the title of the paper suggests, the authors introduce the idea of uncertainty reduction alongside a decision-making approach that can aid in deciding when and where to incorporate uncertainty reduction. This decision aid is necessary as there is a cost associated with reducing uncertainty. Consider the simple example of a system reducing some uncertainty by pinging a server to see if it's alive. This task consumes resources, both physical and temporal, as does most other forms of uncertainty reduction. In order for uncertainty reduction to be fully exploited, the authors identify two necessities. Firstly, a catalogue of uncertainty reduction tactics accompanied by formal descriptions of their costs and benefits. And secondly, easy-to-use reasoning mechanisms that allow uncertainty reduction to be incorporated alongside existing uncertainty management models. To aid engineers in designing systems with uncertainty reduction, the authors provide an example of how implementing uncertainty reduction into a system can actually reduce the average cost of an event, despite the reduction tactic always having its own associated cost. So let's have a look at a corporate system comprising a web server, which we'll call server A, and a database, which we'll call server B, which focuses on self-protection against a cyber attack. The diagrams used here are Markov decision processes. So let's say there's an intrusion detection system, or an IDS, which has just raised an alert stating that there's a 30% chance that server A has been compromised by some unknown party. This is represented in the diagram by the 0.7 probability that both A and B are actually fine. We also add a small probability of 0.075 that the hacker will immediately compromise server B if we take no action, leaving a chance of 0.225 that A has been compromised, but B has not. The system can either choose to restore server A from a previous unaccompanied backup, on the restore A arrow there, which has a cost of 50, and a 100% chance of resolving the problem entirely. Alternatively, the system can do nothing, which could potentially lead to a cost of 500 from having both servers compromised, as well as 100 to restore both servers later. Statistically, restoring A is the best choice when considering future costs, despite it being far more likely that the server is not compromised. This table shows the values of the probability of A being compromised that caused the decision to change, being 0.267 in this case. Next, consider the same system, but with an uncertainty reduction tactic built in, namely to scan server A to determine whether or not it has actually been compromised. That has a cost of 25 associated with it. Using a similar calculation as before, we see that the best choice is to scan A with an expected cost of 40. Again, this table shows the appropriate tactic depending on the probability of server A being compromised. The result with the addition of a reduction tactic shows significant improvements. For one, the probability of server A being compromised must be significantly higher, over 50%, before the system chooses to immediately restore it, which is a much more sensible value than the approximately 27% for the previous system. The authors identify a few drawbacks to their proposal. Firstly, in reality, it's very difficult to quantify the impact of a tactic. In our example, it was easy, as scanning the server immediately told us either that it was or was not compromised. But in reality, a tactic may only reduce the uncertainty in some information without completely eliminating it, as the scanner did. The impact this kind of tactic has on some information's uncertainty is difficult to quantify. Secondly, a large catalogue of uncertainty reduction tactics, along with their costs and impacts, and written up in a meaningful yet standardized way, must be created for any significant uptake. The authors identify design pattern documentation techniques as useful for achieving this goal. Finally, decision procedures that integrate with regular self-adaptation decision drivers and are fast enough to make these decisions at runtime are needed. The algorithm used in the example works well for small systems, but in complex systems with many possible routes, taking into account future decisions, uncertainty within the tactics themselves, and many other variables, it would not be able to cope. In fact, in large enough systems, this may lead to an NP-hard or even unsolvable, or at least unverifiable, problem. There's not really much to be said here after what the authors themselves have identified. The idea of uncertainty reduction tactics with a cost and impact, as well as the simple algorithm used in the provided example, are very similar to existing techniques in the area of risk management. So it's possible that more ideas could be drawn from that field, or vice versa. Perhaps a system of this nature could be applied to risk management for automated risk management strategy creation that adapts to changing requirements and environmental conditions. Thank you.